and things I don't want put on YouTube, because this is where we'll be going. So as an update, I will be uploading these recordings to YouTube now that I finally managed to get access to the club's YouTube channel. So um, if you guys, I'll be sending that link out with the next monthly invite where the AFSIG's playlist is on our YouTube channel. So if you wanted to go back, most of our old recordings are also there as well, but I need to reorganize them, and it's been a crazy summer. First off, for those joining us for the first time, which I see two names I don't recognize, so welcome. This is the Tucson Astronomy Association's AFSIG group, or Astronomy Fundamentals. This group normally tries to keep introductory level topics into astronomy concepts, trying to keep it around the high school level for understanding. Normally we do two presentations, just due to a lack of volunteers, because some of my usual co-presenters are busy with other things outside. I've only been able to have the time to do one. And this month, if the screen share still says it's sharing, I will be talking about the cosmic microwave background. Any questions before we start? If you do have questions during the presentation, you feel free to just reach out and interrupt, or just toss them into the chat, and I will try to get to them as I see them. There we go. So as much as the cosmic microwave background is, one of those like big discoveries in astronomy, it has its origins with the kind of entwined with the Big Bang theory itself. It begins in the mid 1920s with a Belgian Catholic priest by the names of George Lemaitre. And he was still in this time that the church would engage regularly in astronomy activities. And during his education, he wound up as a research assistant at Cambridge University in the UK, and became colleagues with Arthur Eddington and Harlow Shapley, who we've talked about in some other presentations, and we've actually given a presentation on Arthur Eddington. Arthur Eddington was essentially one of the giants of his day, being the astronomer who provided the crucial evidence that would confirm Einstein's theory of general relativity. So meeting these were not insignificant colleagues. During his time at Cambridge, he had a little bit of a thought experiment. And 2 years before Hubble would release his paper that made him famous, he actually proposed what we now know as the Big Bang Theory. And in his thought experiment, he basically derived what we now know as Hubble's law and the Hubble constant prior to Hubble, and recognizing that the universe was expanding within this work. And unfortunately, like all many strange quirks of history, that there will be a couple more in this presentation, he published it in a journal that was only ever read by Belgian astronomers. So this didn't go anywhere, didn't gain any international fame or any attraction. I need this because that may have some speaking notes. There we go. So with Lemaitre's work kind of hanging in the background here, we move on a couple years down the road with Edwin Hubble. We also have done a profile on him that's much larger than I'll fit into this presentation. But his paper that eventually found out, hey, the universe is expanding, was a really big deal. But there were some sticking points into his paper. namely being that his math showed uh, and that the universe, as he measured it, was too young. It didn't jive with some other pieces of evidence that we had already found. For instance, Hubble's initial values for the age of the universe projected it to be about roughly 2 billion years old. But we had already seen from radioactive dating of uranium, which, with Marie Curie during this time, study of radioactive materials was, growing. And that we'd already found that the Earth, at least, was, 4 billion years old. And by also examining globular clusters that we see in the night sky, like our good friend Omega Centauri that we see in Tucson every spring and then wave him by, that those clusters were estimated to be on the order of about 10 billion years old. So, slowing this age discrepancy helped slow some of the adoption of Hubble's work until as more evidence was built to establish that what he was seeing was correct. During this time, as astronomers, as his work was beginning to get more and more solid evidence, we're fast forwarding about 20 years here. There'll be more pictures in this presentation, I swear. That a group of astronomers were, puzzling over, how can we reconcile, this expanding universe, because Lemaitre's work, which, he had, moved over, he had in the intervening years published into a more prominent journal after Hubble's work, which did suggest that maybe the universe had a beginning. And like many people with strong religious beliefs, they didn't like that. They liked the universe to be eternal. And so they set about trying to make theories that say, hey, how can we have an eternal universe if the universe is expanding? And so that eventually led to two papers from two different groups, a new model for the expanding universe by Fred Hoyle, and then the steady state theory and the expanding universe by Hermann Bondi and Thomas Gold. Their essential argument, in order to, counteract the expanding nature of the universe, was that somehow new matter just appeared out of nowhere. Not, the exact mechanism, obviously what some of us may recall from, the conservation of energy, the law of the conservation of energy and all these other fancy physical laws that say, hey, you can't really create something out of nothing. Was one thing I'm not quite sure how they ever would have gotten around. But in order to, maintain the universe in its state, they projected that, you'd have to have roughly one hydrogen atom per cubic meter per 100 billion years, which is kind of hard to fathom, just a cubic, just, a random hydrogen atom popping up on our solar system every year in order to maintain the expansion. So that was an interesting little thing. But setting aside some of the what we might now call questionable physics, this theory had set some limitations on what we should be able to observe with certain things in the night sky, namely extragalactic radio sources such as quasars. Another interesting quirk of this work is that they also ended up projecting that the age of an average galaxy in the universe was 1/3 of Hubble's measurement for the age of the universe. So essentially what they were saying is that, well, if the universe is eternal, then the universe is, however, then any galaxy in the universe is on average 700 million years old. And, going back to what we just said, if the Earth is 2 billion years old, where did our galaxy come from in the last 700 million years? So some interesting questions they would have had to resolve from this. If for those who may have heard more about the Big Bang in other places, Hoyle is the one who would actually eventually coin the term in 1949, and that I do apologize for the typo on that slide. here is a picture of the three astronomers with Hoyle on the left, Thomas Gold in the center, and Bondi on the right. I'm not quite sure what years these were taken in. So, excuse me one second. So so while Gold, Herman, and Bondi were publishing their work in 1948, we have to circle back about 3 or 4 years again, and swing by the Soviet Union for a moment, or a Soviet physicist named George Gamow. He fled the Soviet Union, I think sometimes in the 1930s, mostly to escape because he was displeased with Stalin's regime at the time. This was before World War II had fully gotten underway. And he was studying how elements heavier than helium became abundant in the universe. And I have abundant in quotes because most of the matter in the universe that we can see and recognize is either dark energy, dark matter, hydrogen, or helium. And that makes up like 99.4% of everything. So that's why there's a quotes for abundance there. But in order to do his work, he needed some expertise in nuclear physics. He had fled to the United States at this point. I should have clarified that. But due to World War II at this time, all those nuclear physicists were stuck out in the Mexican desert working on the atomic bomb. So he had to go hunting. So basing his work on the fact that on Hubble saying that hey, the universe is expanding, he, like Lemaitre, decided to say, well, if the universe is expanding, let's just reverse it. And he used that to try to figure out how the universe would change in terms of hydrogen, helium, and other elements as this expansion was run backwards. And during this work, he would recruit PhD student Ralph Alpher in order to help with the physics calculations. And to go with this, he was also conveniently able to use some of the first computers. And being a software engineer, this is always an interesting thing to see where early computing comes into play, that were becoming available after World War II, like the Emacs computer, which, by our standards today, your phone is more powerful than most of these, but regardless. So on the left here, we have Ralph Alford, and on the right, we have George Gamow. So eventually, when they finally got to a point where they could publish their work, Gamow noted that making Ralph Alford the lead author for his PhD thesis, noted that this particular paper was going to be published on April 1st. And he had a bit of a sense of humor. And he decided to add one of his other colleagues, known as Hans Bethe, as a gentleman's joke to the list of authors, because he noted that the paper's and author's initials would then be the first 3 letters of the Greek alphabet. So there was a little bit of contention on Alford as a PhD student. He was, just coming out of his thesis and was wanting to make a name for himself. And I'm hoping I hit record. 1 second. Okay, good. Oh, oof. I almost had a heart attack and thought I forgot to hit record. Sorry about that. But as I was saying, Alfred was trying to make a name for himself with his thesis. Like all people coming out of college is like, hey, I need to get a job. And Hans Bethe was, much more experienced in this field. And Gamow was Alfred's advisor. And so he was hesitant he really didn't want Bethe on the paper just to overshadow his own accomplishments. And it may very well have contributed to something we'll talk about in a bit. So the paper was eventually published as it was, with the name The Origin of the Chemical Elements. And while they didn't really get very far in terms of establishing what we now know is the nucleosynthesis model, this paper did actually predict relatively accurately where the concentrations today of hydrogen and helium, and at least getting their proportions correct within the universe. And during Alpher, who was, again, this was serving as his PhD thesis, so he actually had to defend the paper. There was a comment that was made by Gamow at some point that required Alpher to publish a correction or an extension. And Alpher sought out another colleague known as Robert Herman. And what this correction turned out being the more important part of it, because this is what actually laid the groundwork for at least outlining what the cosmic microwave background was, in terms of, we should be able to see this faint level of radiation. And it also made a prediction about, where the signal would fit in the range of the radio spectrum. So working with more complicated math on radios than I will be able to explain, they determined that the temperature of the signal, and there's apparently a correlation between temperature and radio frequency for microwaves or other or lower frequencies, that they determined that this signal would be around 5 Kelvin, just 5 degrees above absolute zero, which at the time placed it into the microwave band, hence what we're talking about here tonight. But you may think, oh, okay, that's easy to go about, but please remember that at this time radio astronomy was still very much in its infancy. So even though they had detected this, they weren't quite sure the technology yet existed for them to be able to measure it in the first place. And Ralpher and Gamow were mostly theorists, so they just called it there and didn't go look for the signal. Okay. Next slide. There we go. So now we move on to briefly introducing two gentlemen. The first is Arno Penzias. He and his family fled Germany in 1940 in order to escape the ongoing Holocaust, eventually making their way to the UK before eventually settling in New York. Penzias would eventually graduate from the City College of New York in 1956 with an undergraduate degree in physics, before going to serve on as a radar officer, which would earn him the opportunity to pursue his PhD at Columbia University, which he earned in 1962. His advisor at the time was Charles Townes, who was also the inventor of the Maser, which is essentially a microwave version of the laser. And we also have Robert Wilson, who was born in Houston, Texas. I couldn't find an exact date on it, despite he's a Nobel Prize winner. He got his undergraduate degree from Rice University, also in Texas, and his PhD he earned from California Institute of Technology. He had two advisors over the course of his PhD. The first was Martin Schmidt, who his notable achievement was he was the first to measure distances to quasars. And John Bolton, who was at this time one of the active initial pioneers in getting radio astronomy recognized as an actual valid form of astronomy outside of the visible light spectrum. So both of these gentlemen clearly had some expertise dealing with radios and microwaves as part of their schooling and initial research work. And the two would eventually meet up. So Penzias, after graduating, would go on to join Bell Laboratories in 1963. specifically out of New Jersey. And Penzias had met about names. Wilson, thank you. During this initial grounding in phase and, looking for work and what was available to him in order to say, hey, I want to do these such and such experiments. And the pair eventually settled on, working with cryogenically cooled microwave detectors in order to map neutral hydrogen. I couldn't really, in the time I had, I couldn't find why they were wanting to map neutral hydrogen. I'm not quite sure what it was contributing to astronomy at this particular point in history. But I'm thinking it has to do something with star formation or some other portion about the age of the universe at the time. But I could be very mistaken. So to get their experiments off the ground, they would end up borrowing a radiometer that was in New Jersey. That was also built by Bell Labs at the tail end of the 1950s. That was used as part of Project Echo. This was one of NASA's, which I don't even think it was called NASA quite yet at that point. This was one of an early demonstration for satellite communication, and Bell Labs contributed the antenna in order to detect signals from these satellites. So it was working, and it would detect, it wasn't starting from nothing for this pair. And so they just took, since the antenna was in use and Bell Labs still owned the site, they just took it over and they did some revamping on it. I'm pretty sure many people on this would have seen this picture in other sources. This is just a brief image of what the antenna looked like, the distinct bell-shaped horn that is unique for this discovery and very unusual. So after getting their instruments installed, their cryogenic cooling in place, they began receiving signal and they sent about doing their work. In order to map the neutral hydrogen that they were intending, they needed to account for all other sources of microwave noise that they might encounter. And over the time, as they started paring away sources, the next slide, we'll talk a little bit more about some of the things they had to deal with. They eventually found that this faint microwave signal was everywhere, at all directions. And they would spend months ruling out these other sources. Things like they determined that the signal that they had wasn't noise. It was real. It was coming from everywhere. And struggled to think, like, what is this? Where is this coming from? Until a rather interesting chance meeting that Penzias had while on a plane, where he chatted up another astronomer. I'm not quite sure how the two wound up on the plane or where they were going. I couldn't find that. Or they presumably may have been going to a conference. But Penzias met Bernard Burke, and Bernard Burke had told Penzias to reach out to astronomer Bob Dickey at Princeton University. It turns out that Dickey was, having seen some of the other work with the Big Bang Theory and also familiar with Ralph Alpher's work, had actually started to gear up building his own detector specifically to target the cosmic microwave background. And Penzias and Wilson had beaten Dickey to the punch without even knowing that that's what they were detecting. One of the famous quotes that Dickey reportedly came in and told his team after he had gotten off the phone with Penzias was telling his team, quote, "Boys, we've been scooped," saying, that famous, like, despite this, the two teams actually had different expertise, with Wilson's team having much more background in the theoretical aspects, and Arno and Zayas and Wilson just having the experimental results. So the two teams jointly collaborated to publish their works together on the same issue of the Astrophysical Journal. Wilson and Penzias ended up going with a rather interesting title, A Measurement of Excess Antenna Temperature at 4,080 MC per S, which I'm not quite sure what unit of measurement that is. I actually managed to track down this paper, and you would think there'd be a lot more into it. And if you didn't have the background, you'd just be looking like, what am I reading? Because all it says is just, we just found a whole bunch of microwave noise at these temperatures with these considerations for noise that we managed to rule out, and these calibrations for measurement errors. It's basically the crux of their paper. It's a page and a half long. Yes.
Tell him.
Okay, MCS would now be called megahertz.
Okay. Thank you, Vince.
You young guys just don't remember that.
Hard to remember something from before I was born, Vince.
Yep.
Thank you. So, but the paper itself is basically a page and a half long, and it very, very unassuming. You would not think it would be as significant as it eventually turned out to be, without a lot of other background noise, without a lot of background expertise in the area. So, as I mentioned, the team had to rule out a bunch of things in order to make their claim before they felt comfortable coming forward with this claim. And at least two of the sources that they had to rule out were, microwaves potentially coming from, nearby New York City, I think, which was like 50 miles away. They also had to deal with pigeons who would routinely nest in the antenna. Had to clear those out on multiple occasions, because they were thinking that perhaps their droppings were, adding noise to the detector. Also, double checking and triple checking their equipment to see if maybe it was not a signal detection, but maybe a leak of signal from equipment somewhere else that was getting into their detector. They ruled all that out. And then what they also noticed, as this was before the meeting, the call with Bob Dickey, was that they were detecting this signal uniformly in the sky all year round at any time of the day. So, excuse me. And it was very uniform. As I mentioned, there's a relation between, which I'm not clear on how to explain, between the microwave energy and temperature, that the signal did not vary at all, at least within the ability of their equipment to measure. It stayed roughly at a consistent frequency with 1 in 25,000 variance across the whole sky. So it was the technical term for that is isotropic, which basically just means the signal was unusually uniform. So with this very unassuming paper, lots of awards were given out. Interestingly, in all this work, when on the initial discovery of the cosmic microwave background, only Penzias and Wilson would actually get the big honors. George Gamow and Ralph Alpher, who did the initial work, that the initial theoretical work to identify that the cosmic background exists, as well as Bob Dickey's team, did not receive recognition on this. They were completely left out. And it's not quite clear why that would be the case. If it was politics or some other factor at the time with the Nobel Committee, it's kind of a bit confusing, because normally they would include something like that, I would think. But in addition to that initial award, Fast forwarding to some other experiments we'll briefly talk about. There was a second Nobel Prize given specifically for the cosmic microwave background that went to John Mather and George Smoot. And their work was for this quote discovery of the basic form and variations of the cosmic microwave background. So they were working on an experiment. Sorry, they were the Mather and Smoot were working on the Kobe satellite, which we'll briefly talk about near the end of this presentation. But just keep their names in mind for a brief sec for a good bit. So with that, we've managed to detect this signal. It needs to ask what exactly created this signal. Why was it important? We've only mentioned like, hey, this is something that would help identify that the Big Bang was a valid theory. That steady state theory that was being pushed by Hoyle was true, was not the way to go. The Big Bang theory was how the universe created. It did have a beginning. So we need to talk about, what formed it. So very early in the universe, it was very hot and very dense. And in the first about 400,000 years of the universe's existence, it was too hot and too dense for light to travel at all. Think of it as being inside of a gigantic blender full of basically tar. Nope, nothing could get anywhere. And eventually, as we come across the 400,000 year mark, the universe would cool below a certain point. This particular point temperature happens to be around 4,000 Kelvin, which is roughly the surface temperature of a red dwarf star. And eventually, this would allow light to travel. There's some other things I'm leaving out in here in terms of the Big Bang Theory, which just for sake of time, I'm not going to go into. But during this intermediate transition, the photons began the ability to travel in the straight lines. Before this isn't kind of rehashing. They would just bounce into other nuclear, this this hydrogen and helium soup, and they would get absorbed and by those nuclear atoms and turned into electrons and then re-emitted as more photons continuously. So just from the density of the primordial universe. And so this characteristic of the universe being opaque at this time essentially means that in optical wavelengths, basically anything in the electromagnetic spectrum, that the cosmic microwave background is the farthest back in time in the universe's history that we can see. There's only two things that we currently have that we know about in physics that would potentially allow us to see farther than this, the cosmic microwave background. And they are both gravity waves, which we've only recently begun to be able to detect, and neutrinos. Neutrinos being because they basically interact with nothing, and physicists hate them for a lot of very annoying reasons, which was an amusing article I read some time ago, but we won't get into that. Nuclear physicists do not like neutrinos for many, many, many reasons, which is beyond the scope of this group. So, as I mentioned, universe go down. So I'd ended up covering this entire slide, not being able to read ahead. Only thing that take away from this one is that with the cosmic microwave background being photons from it linger all around us. It's not some invisible wall, near the edge of the visible universe that we can see. And photons from the cosmic microwave background are in front of us right now. And the current estimates put around 400 photons in front of you every cubic centimeter of space. Excuse me. Are photons that originated from the cosmic microwave background 13.8 billion years ago, which is kind of like one of those things. Is like, if I have this glass of water, how many atoms of hydrogen were drunk by a dinosaur? Question. So, that unused. So, uh, after Penzias's discovery, it took a couple more decades for us to get any more information on the cosmic microwave background, and it begins first with the cosmic microwave a couple of space missions that were launched jointly by the NASA and cooperating partners in the European Union, beginning with the Cosmic Background Explorer, which was launched and operated between 1989 and 1993. And am I still connected? Can I get a mic check real quick?
Yep, you're good.
Okay.
Yeah, you're good.
My other screen completely changed, and I thought Zoom crashed or something. Then following Kobe was the WMAP satellite, which operated from 2001 to 2010. And then most recently, the Planck satellite, which operated from 2009 to 2013. All three satellites, their sole goal was to map the cosmic microwave background, each satellite getting finer and finer resolution of this signal. Because it turns out, despite what Arno and Wilson initially detected, with this signal being very uniform, there are variations in it, and its temperature, extremely small variations. Excuse me. And without likely dealing with equipment limitations of their time, these are just not detectable. They're incredibly precise, which is also the reason why these three missions are space telescopes and not ground-based telescopes, just eliminating more significant sources of noise and allowing for more precise detectors. And so, come on, next slide. So each satellite would go on to contribute finer and finer resolutions to the cosmic microwave background. In the top right here is essentially how if you had mapped the data that came from Arno and Wilson's initial detection, it would eventually have just been a single solid color on a circle graph. You couldn't really see any of these variations until you would get to Planck and WMAP, with each of these satellites contributing finer and finer details, with red being slightly warmer areas and blue being slightly cooler areas within this signal. Again, this signal is almost entirely within about the 2 to 3 Kelvin range. So what these satellites were detecting was a variation of like 100,000th of a degree here in this map. So very, very subtle. And here are briefly images of each of the satellites that we've used since then. And to wrap that up, because it seems kind of abrupt here in terms of like, well, we've talked about detecting it, but what really is this contributing going on into astronomy as a whole? Because it's still an important aspect of the study of cosmology and the Big Bang Theory. And I couldn't really get anything solid that would have been explainable without a lot of way over my head sort of stuff. So it's still one of those phenomena that's being actively studied for many reasons. And not quite sure where the astronomy community will go to from there in terms of studying the cosmic microwave background, or if they said we've had enough of this signal here. But it's still very important in laying out, the history of our universe as a whole. Any questions?
Hey, Connor.
Is that Vince?
Yeah.
It's Vince.
Yep, go ahead.
A little history on that big conical antenna.
Mm-hmm.
Bell Labs, of course, killed Jansky's early work on the radio astronomy. And so when these guys came along and realized that would serve their purpose, Bell Labs was all too happy to comply and gave it to them. And I think he even gave them some money to work with it, just to atone for that early quashing of radio astronomy. That antenna was built as the early communication satellite. They had a whole bunch of big balloons going up and reflect. But Hughes Aircraft down in El Segundo leapfrogged everybody and came through with the synchronous satellites, which we use today, and that became very quickly obsolete. And so that's where all the pigeons came from, because that thing, I think, laid fallow for about 20 years before they got to it. I'd have to go back and do some of the research you did.
As from what my slides were, the satellite,
Yeah, I'm still alive, guys.
yeah, where was it? The antenna was in 1959 was when it was used for Project Echo, and they made Arno and Wilson made their announcement in 1968. So it wasn't quite 20 years. It was almost a decade.
Yeah, but I mean, it was left sitting there when the pigeons found it. And they evidently it's quite a mess to clean.
Yeah, so they I didn't actually put the date on here. So the Penzias and Wilson published their discovery in 1968 and then won the Nobel Prize for it in 1978.
That's about how long it takes.
Yeah.
I think it was some back of the room politics that united from Dickey and those guys.
That's what I got to, but I didn't really see anything conclusive.
Well, they tend not to publish that kind of stuff. It goes back to when Einstein was delayed a Nobel for so many years. The formation, the Nobel Committee was by a bunch of experimentalists. And what's this theoretical guy doing, especially since he's just a, patent office clerk? But that's an interesting story all by itself.
Thanks, Vince.
Now I'm feeling better, I could probably give a talk on that.
Oh, reach out to me. We can talk.
Yeah.
You can certainly use more presenters occasionally. Glad to see you've been doing well.
Yeah, I'm gonna come back. My companion here, the nurse, has got me back.
Glad to hear. Any other questions or comments?
Yeah, I've got a couple of questions.
Go for it, Tom.
Okay, so my understanding is that what we can see of the cosmic background radiation is that it's microwave energy at this point in time. But what was it when it actually occurred, shortly after the Big Bang? My understanding is that first you got protons and things, and then you got hydrogen, and that release some light. Is the cosmic background radiation that we're looking at here the
So-
light that
so it
occurred
is
at
light.
that point in time?
So it is light. So microwaves is part of the electromagnetic spectrum, which is basically it's
Mhm.
carried by photons. So it's always been quote unquote light. Just so the term radiation, at least is one of those weird, not
Yeah.
kind of a misnomer in a sense. In terms of like when people think like, hey, it's radioactive. It's not. It's just light, like like UV rays. UV rays is essentially a form of radiation, but it's not like, going to, kill you. Well, hopefully. Like nuclear explosion sort of thing. So
So
It-
we
it-
see it as the microwave.
so
be- be-
in
yeah,
when the universe was really hot, it was much higher in frequency. Because so it was probably it was very much in the visible light, possibly into the UV spectrum, sort of the light spectrum. But as the universe has expanded with redshift, that light signal has been stretched in frequency so that it has downshifted from those higher frequencies all the way down into microwaves, which is below infrared.
right.
So
So it is it down into that range of the spectrum because of the stretching or because of cooling, or is it kind of one and the same?
that's an interesting question, and I think it's um it's a bit of both, because if you think back to the ideal gas law, that as volume increases in a gas, because essentially this was from a gas, the temperature itself will decrease. So without having a strong physics background, it's probably a combination of both. Uh, at least from an initial standpoint, that there was a lot of cooling from expansion of the universe, just from the volume change. And then once it had expanded enough, then mostly turned into its temperature it became attributed to changes due to redshift.
Gotcha. Okay, so now sort of a different question. The distance thing. My understanding is what we see is from they used to say what 14 billion years. Now they're saying like 40 billion years ago or something like that.
That So the 13.8 billion versus 40 billion is more of astronomers being really annoyingly technical in terms of the observable universe versus the visible universe, which you would think that they are the same thing, but to astronomers they are not. They represent different areas of space.
Mhm.
So
So what we're seeing is that only from the 40 billion years ago. I'm going to presume that
So
any
it's-
sort of radiation that occurred in our immediate vicinity, those photons are long gone and we don't see them anymore. If we did, we'd see them as light, I guess, because they wouldn't be stretched out over that long distance. But so I'm assuming we only see what's really, really far away.
that so the cosmic microwave background, the photons that make it up, are pervasive throughout the whole of the universe. So there are photons, although minuscule amounts of them, even throughout our whole solar system, that are left over from that signal. There's just not a lot of them, and and it gets easier to see this volume of them as you look farther and farther into the past, because it's just the signal itself comes from everywhere in all directions. Now, to quickly make a small correction, it's not that it's with that 40 billion figure. That's not saying that the universe is 40 billion years old. What that is saying is that because of how inflation and expansion of the universe worked, that the volume of the universe that we can quote unquote see due to a lot of technical factors in physics that I can't really explain well, that volume of the visible universe, the observable universe is 40 billion light years.
No, I
Um,
understand. We are moving away.
Yeah.
Yeah,
So it's not that, so
but
not
they're
that
moving away too, so the distance is farther. No, I understand that part. It just seems to me that, you know, if there is background radiation going through our solar system, well, the Big Bang was an awful long time ago. Why is there anything left that would have originated here where we are? It'd be long gone, and maybe somebody 40 billion light years from us can see it, but we can't necessarily see our own here. That's what I'm
So
trying to
it's not that those
grasp on.
photons that are lingering around us, that 400 photons are, from our section of the universe. What it's saying is that these photons that are traveling in from all directions, that about 400 of those photons, could have just got wherever they originally came from and just got to us. About 400 of those are from the cosmic microwave background, whether they were created in our solar system, which they most certainly were not, because they, to your point, would have gone off in some other velocity, but those photons may have come from some other section of the universe and are just now getting to us,
Okay.
and so in that volume is where they're coming from.
Okay. Yeah. That makes sense. Yeah. That clears it up. Thanks.
Good questions. Anybody else? Questions or comments?
Good job, Connor.
Thanks.
Thank you.
I'm gonna go ahead and end the recording here for the month. And before we go,